Hi, the video you've selected is regarding the ATCC Overview webinar that was presented on March 10th at 8 a.m. by Scott Evans, EDI's CTO. This will be an overview of the development and advanced functionality of the ATCC cabinet components that are being provided by several controller and cabinet manufacturers. We hope you enjoy the video.
Going to introduce Scott Evans. He's our Chief Technology Officer with Eberle Design, and he will be presenting the ATC cabinet overview today.
All right, thank you, Matt. This is intended to be really a cabinet level overview. Eberle Design makes many of the components that goes in the cabinet. The purpose of this overview is to introduce the cabinet to those of you that don't yet know what it is. It's an industry effort to create a new architecture. So hopefully in this 1 hour session, we'll give you enough information to generate some interest and questions and a need to look further. So as Matt stated, if you have particular questions, whether they're technical or otherwise, if you can send them to us through the GoToWebinar toolbar, we will compile them at the end of the presentation and kind of publish all the questions and answers. So having said that, the agenda really is just a quick introduction. I think it benefits to have a little overview of how we got to where we are with this particular cabinet technology. We'll talk about the development path, and really the core of the presentation is what are the features and the benefits. Why should I, as a user agency, be interested in an ATC cabinet? And then I'm going to highlight not all, but a few of the assemblies and components that are kind of new to the ATC cabinet or central to the advantages that we're going to refer to. So this is a good picture of one particular implementation of the ATC cabinet. It's in a 332 type shell. The cabinet is basically designed as an open architecture, hardware and software. It's based originally on the ITE NEMA AASHTO ITS cabinet standard. That's a published national standard, and again, ITS cabinet. So the advantages of this cabinet in general, and we'll get into those deeper later in the presentation, I think you'll find that there are significant improvements, and I underscore significant, to cabinets that we're using today, whether that's NEMA TS1, TS2, 332, ITS cabinet, so forth. Modularity is important. Compact size is something we hear continuously. I either need more equipment in the same space, or I'd like half the space with the same equipment. Motorist safety is always paramount. We'll see a number of improvements in this cabinet architecture dealing with motorist safety, technician safety, and of course diagnostics. So keep in mind that these cabinet types I mentioned in the bottom bullet point, Caltrans 33X hardware is 38 years old. Even NEMA TS2, which was first published in 1992, is now 23 years old. So while this industry moves slowly in some regards, we have the benefit of using mature technology. So the point of the ATC, one of the points of the ATC cabinet is to try and adopt all of the, or as many of the best features of these cabinet architectures and roll it into one new architecture. So as you can see from this little picture, we've taken, for example, from the Model 170 332, we've adopted the rack mount concept. From NEMA TS2, it's a serial bus based cabinet, so it's easily expanded, easily interconnected. We're not limited by point-to-point wiring and massive connectors and cables. From the ITS cabinet, we've taken a lot of the modular assembly notions and the basic backbone of the serial architecture. And the fourth leg of the stool there, if you will, is we've adopted some new modern technology. We've been stuck in time, if you will, with load switches driving LEDs, for example, load current monitoring, things like that. So we've taken all of these features and tried to adopt as many as we can into what we're calling the ATC cabinet series. So to be clear, the ATC standard is a component of the ITE NEMA AASHTO joint suite of ATC standards. In the original version, we have the ITS cabinet standard V1. This effort grew out of what can we do to that version 1 to improve it and bring it up to a level that's a benefit to our industry. So while the ITS cabinet standard was published back in 2006, seems like just yesterday, work started right away on what can we do to improve it. And this was originally defined as ITS cabinet version 2. We decided that the name would be better reflective of the suite of standards, the ATC standards, if we called this cabinet ATC instead of ITS. So you'll find both uses of the name, but consider ITS cabinet version 2 is been renamed to ATC cabinet. Much of the work that went on in this original work project, this was funded by the Federal Highway. It was a joint committee project to develop version 2, and the main goal of the project was to refine what we learned from version 1, and believe me, we learned a lot of lessons there, and also to start considering a move to low voltage DC operation in cabinets. So in 2011, we were marching along. You can't probably see the detail. This is the beloved V diagram of standards development. But we had pretty much defined the architecture. Again, it was a modification of the version 1. We had much of the detailed level defined, the CONOPS, the systems requirements, things like that. So unfortunately in 2011, this working group, along with quite a few other NTCIP standards efforts, lost funding from the feds, and so the working group was kind of put on hold. 3 manufacturers decided to continue the program on their own and bring forth prototype cabinets, finish the design as best we could. So it's been done since 2011 as kind of an informal cooperation between manufacturers, moving along without the benefit of a formal working group. So let's talk about what the cabinet is. Again, some of the design objectives originally were, let's address compact size. That's always important. I touched briefly on LED signal compatibility. Again, we've been stuck with 10 amp load switches that are not LED compatible for quite a few years. Standards are hard to change. Backward compatibility is hard to deal with. But I believe today the vast majority, if not all, signal heads are LED. There may be a few yellows running around and incandescent, but it's important that we bring the driver technology up to par with the load technology, LED signals. Technician and motorist safety is always important. Anything we can do to improve operation there is a great benefit. Modular, rack-mounted, we'd like to be able to configure cabinets for their optimum use. If it's a ramp meter or a small CVD style cabinet, it's nice to have options that we can easily adapt to. The flip side is, how do we accommodate large or what I see quite a bit now is running multiple intersections off the same cabinet hardware. So we have a wide variety of applications we'd like to meet, and when you take a modular approach to these cabinet assemblies, it makes that much easier to attain. And finally, low voltage operation. This is kind of a work in progress. Low voltage operation satisfies some of the needs of technician safety. We'll talk about that in a little bit. It has some dramatic engineering benefits, hardware costs, and power savings, things like that, which we'll touch on a little bit later. So size does matter. Here's kind of a fairly equivalent comparison of a 332 style cabinet on the left and the equivalent, for the most part, ATC version on the right. So you can see that we have a number of terms bandied around here: high density, double density. We pretty much have the equivalent amount of functionality in approximately half the space. It is a 19-inch rack format. We are looking at other formats for different applications, perhaps a 14-inch rack for a CBD configuration, single door, double door, quad door. Again, once you adopt the notion of modular assemblies, it becomes relatively easy to create new ones for special applications or reconfigure to most efficiently satisfy the application that you're trying to address. So in pretty much all of the racks, we've defined these high-density components. In the cabinet that we're showing to the right there, that's the 16-channel output capacity. The very bottom rack there is the output assembly. It has 8 2-channel load switches in it and the monitoring system. There's also a 32-channel version defined that would essentially add another 4.5-inch rack to bring a second assembly of load switches out there. So we can accommodate 32 output channels. For inputs, if we consider conventional loop detector style cards, we have the ability to handle up to 120 channels. What's shown in the picture there, again, is 2 input files. The standard setup is 24 channels per rack, so we're showing 48 channels there. We also have a quad density input file defined that in the space of one rack, we can load it up with single width 4-channel loop detectors to get 48 channels in the space of one conventional 4.5-inch rack. So size does matter. If you want to put that amount of equipment in a very small cabinet, you could do so. If instead you have needs for other equipment, maybe it's batteries for your DBS system, communications equipment, masters, other things like that, as you can see, there's lots of empty space. So let's talk about LED signals. People often describe the ATC cabinet as a low power cabinet. It's a little bit of a misnomer. The cabinet equipment itself is very much more efficient than our conventional equipment. We don't have big low switches with aluminum chassis to dissipate the 1.5, 1.8 watts each that we generate in heat. So there is an efficiency to be obtained within the cabinet, and I'll add that any amount of heat that we can not generate in the cabinet just increases reliability logarithmically. But really my point here is that this technology is really an enabler for higher energy use. The bulk of the power that we dissipate at any cabinet assembly is the signal heads. And while we took a major step going from 130 watt incandescent bulbs to 12 watt LED signal heads, we're now looking at the possibility of reducing those 12 watt heads down to what I call ultra low power LEDs, maybe in the 1 to 2 watt range. So The magnitude of the improvement isn't quite as dramatic as it was when we got rid of incandescents, but we'll find that this really starts putting battery backup systems into a more cost-effective range, a more practical range. We'd always like to reduce the amount of batteries that we need to stack in a cabinet, cost, maintenance, size, all of those issues. So this is just a quick note just to put it in perspective. As you can see, and it's kind of a graph on the right there, trends in power required for LED signal lamps. And as technology has marched on, what we're showing there in the red is essentially wasted power, even in our quoted high-efficiency LED signals. The wasted power is purposely designed into conventional signal heads because manufacturers of those heads know that if they go below approximately 7 watts, they're going to have compatibility issues with conventional triac-based load switches. So as you can see there in that 1 and 2 red area, that's power that we could eliminate right now by going to the load switch technology used in the ATC cabinet. And again, I'm expecting by the time we move along and manufacturers start developing signal heads designed for this new technology, we'll be down in the 2-watt range in not too long. So it's an enabler for this low power, and within the cabinet, we're also generating less heat and wasting less power. So the second important feature here, or third, is motorist safety. Motorist safety is always in our business kind of the number one, job number one. We've made a number of significant improvements. Load current monitoring has been added to the monitoring system, so we now know what the signal voltage is, and we know what the current going to the signal loads is. And we can detect, for example, if a field wire were to fail or get cut, we detect now a dark approach to the motorist immediately. In current systems, we have to wait for the signals to cycle to the next color, and we kind of detect an open load condition in an obscure way using dual indication monitoring. So load current monitoring brings an important piece of the puzzle together, one that I think we've been, I won't say ignoring, but not putting much attention to for the past 20, 30 years. There's a number of other, I'll say less significant, but probably equally important, what I call fail-safer design techniques within the cabinets. For example, when the cabinet goes to flash, we have a concern about if there are shorts in the field wiring or our main contactor fails to transfer. Kind of two problems happen at the same time, 2 points of failure. We would like to ensure, above all else, that all motorists see is flashing red. So we've gone to a number of steps within the cabinet to ensure if that situation were to happen, we can disable load switch outputs, we take away the 24-volt input, and we do our best to make sure that even in the face of 2 failures, we still provide emergency flash mode. A couple of other points here. The flasher has been moved out of the assembly, out of the output assembly. It's now located down in the service assembly, such that in an ATC cabinet, all assemblies, all components of the cabinet, except for the service assembly, this is the module where power comes into the cabinet, we have our main breaker, and our field termination assembly panel, however we have that connected, we need our field wires hooked up. We can replace all assemblies within the cabinet and leave the intersection in flash. So that's a significant improvement for motor safety when we're maintaining an intersection or trying to repair a malfunction. Cabinet's also designed to prevent failures. We have pluggable surge protection on the mains input, inputs, and outputs. And while surge suppression or surge protection is nothing new, this notion that it's pluggable, I believe, will help ensure that as part of a preventive maintenance effort, technicians can easily test that the protection is still working, it hasn't been damaged. That's one of the drawbacks of parallel surge protection is if it fails, we may not know it's not working any longer, and then when we have a lightning hit or a voltage surge, something like that, we end up damaging equipment that should have been protected. So it's an important feature to be able to test that kind of protection. Surge suppression is a geographic issue, but if you have it in there, we'd like to make sure it's doing its job. So let's touch on technician safety as well. There is a pretty strong push in the industry today to address the issue of technician safety. This is in terms of accidental contact. We have now a lot of people poking their heads into cabinets. Maybe they have neckties on, things like that, that aren't electricians, aren't perhaps practicing technicians that know how to work around high voltage. We'd like to protect those people from accidental contact. So a great deal of attention has been paid in laying out the cabinet such that there are no easily exposed high voltage contact points, things like that. One of the advantages of this notion of low voltage cabinets further promotes that whole notion. When we keep all of the voltages within the cabinet below 50 volts, we now enter a different realm of technician safety, and we avoid a lot of the issues of requiring protective personnel equipment, face guards, leather boots and gloves, and the moon suit kind of concept. And I think Caltrans is headed down that road. So they're well aware of issues that can deal with. In some areas, it's noted that for anybody to even open the cabinet door and go in and push a button or replace a card, you have to be a licensed electrician. So local requirements like that might also be eased by this move to low voltage operation. So it's an area that we're kind of moving into. I think we're going to learn as we go other benefits and other attributes of going to low voltage. It is a radical change for users. It affects all of their signal heads. It affects the operation within the cabinet. Perhaps it brings new opportunities for power sources, but I believe it will offer efficiencies as well in battery backup systems and where we get energy to run cabinets during off-grid periods, hurricane evacuations, things like that. Fuel cells, windmills, solar panels. All of those kind of concepts will, I believe, be easier to adapt to a low voltage type of cabinet technology. So what I'm showing here again, this is an example of a cabinet that's currently built today using the low voltage components. One of the main points here is that the cabinet architecture and the actual design of the cabinet, we have already built in the hooks, if you will, that we need to run low voltage. So rather than an add-on, any ATC cabinet can be run as a high voltage 120 volt system or a low voltage 48 volt system simply by replacing some of the affected components and moving a few wires in the cabinet to bring power into the right bus. So the cabinet is designed moving forward knowing that low voltage operation is a goal of the future to obtain. Much of the internal cabinet wiring, door switches, flash transfer relays, a lot of those internal wiring components are already being operated on a 48 volt DC. So again, we don't have as much high voltage running around the cabinet for shock hazards, things like that. So many of the first steps have already been taken to move towards a low voltage type configuration. Another big feature of the ATC cabinet architecture excuse me, is this modular design. And we're going to see how all of the components of the cabinet are built in this modular, interchangeable, interoperable fashion. So I mentioned earlier, we're able to adapt not only to different configurations, but to new ideas and new concepts. For example, when we move to this new low-power, dual-channel, high-density load switch notion, it only affected the output assembly. All of the other assemblies of the cabinet, the controller, inputs, everything else remained unaffected. So from a design point of view and a deployment point of view, modular architecture is really flexible. We're going to find as we move along different applications that we want to deal with. The CVD cabinet, or a small pole-mounted type cabinet, has been a challenge to develop over the years. Again, with this modular architecture, I think we can come up finally with a solution that will really hit the nail on the head there. But again, we have a lot of different wide applications. We've got a number of designs that are looking at big intersections. You might question, gee, I'll never need 32 channels of output. But we're finding it's not just free flow intersections, but perhaps it's 2 or 3 closely spaced intersections on a freeway exchange or something like that, where coordination is a challenge. We can run all 3 of those intersections on the same controller in the same cabinet, and all of a sudden the coordination issues go away. So a lot of different ways to use the capacity, both on the high end and the low end. If we have a simple application like a Hawk pedestrian setup, again, we have a nice compact solution for that. So let's take a closer look at some of these assemblies and components. Again, here's this is just a drawing of a cabinet, and here we see the big controller. That's a 2070 controller. Below it's an input assembly. Below that is the output assembly. At the very bottom left, where the power comes into the cabinet, that's our service assembly. That has the main breakers, the main surge arrestor, and it also contains, in this implementation, the flasher for the cabinet. So we're gonna see in this picture, and I'm not going to go through the detail of all this, but not only is this a simplified block diagram of all of the functional assemblies, but it pretty closely represents the actual physical assemblies that you'll find in the cabinet. Controller unit, we have a display unit for the monitor, we have a power supply, rack-mounted 1U power supply. We have our input assemblies, up to 5 are defined. Like NEMA TS2, the serial bus provides a real benefit in expandability. If we want to add additional input capability, we install another assembly, we hook up power, we hook up the inputs to the assembly, and we connect the serial bus cable, and we're in business. Below that is the output assembly. That's where we find all our high-density load switches and the monitoring system. We have a field termination assembly. Currently, there's several different ways to do this defined. Conventional termination panels. We have cards that plug into the back of the assembly. Here's where we've got several different possibilities depending on which suits the application the best. And down at the bottom, finally, the service assembly that I talked about. So like NEMA TS2, like ITS Cabinet version 1, All of the little arrows and lines interconnecting these assemblies are the system of serial buses. We have serial bus 1, which is our control bus that connects the monitor to the controller and connects the input assembly to the controller. We have serial bus 2, which is a high-speed synchronous data bus, or asynchronous. It's up to the application, but it's basically undefined at this point, so it's available to be used for whatever the application software chooses to use it for. And then there is a third bus here that is local to the output assembly only, and it's what the CMU uses to communicate with the intelligent load switches. So let's take a look at an output assembly. This is one particular implementation. Within the output assembly, again, we find a card-style CMU, the cabinet monitor unit. We'll find 8 dual-channel 2202 high-density switch packs. What we're seeing in the picture here is the 16-channel version. It doesn't take much imagination to envision a little bigger assembly, roughly double the height, that would hold the other 8 load switches to give us a 32-channel capacity. On the far right of that assembly is a component called the 2218. This is the SIU, very similar in functionality to a TS2 BIU. It's used to convert serial data from the controller to parallel outputs that drive the load switches. And then there's a number of components in there for our main contactor, breakers, switches, etc. So like a 332 style cabinet, we have breakers in the output assembly that protect not each channel, but groups of channels individually. So it provides a little better protection from short circuit damage, things like that, and would also assist the technician in kind of narrowing down where his problem may be depending on which breaker has tripped. Take a look at an input assembly, and again, this is designed with loop detectors in mind. If we're using a different technology such as video or radar or many of the more, I'll say, not card rack based solutions for detection, you may or may not even need this assembly. If that product communicates on the serial bus, it could be mounted in its own assembly and connected up to the controller through the serial bus. If that device is using what we call loop emulation, I/O cards, that kind of thing, then you would install this input assembly. So I mentioned earlier, we won't dwell on this one, it's pretty conventional. We've designed it such that it could accommodate 24 inputs. We have a higher density version that would require 2 SIUs and 4-channel half-width detectors to get a total of 48 inputs in the same space that we now get our 24. So that would be the high-density solution. So EDI produces the components. Some of these will be new to viewers out there, so I thought it'd be good to not discuss all of them, but I'm going to hit a couple that maybe we need to discuss, have an idea what they look like. But this is basically a list of the cabinet components, not including the controller unit, that you need to populate a cabinet with. We have a monitor unit. We have a display unit down there, the 1U on the lower left. We have the high-density switch packs, and all of these components, the ones on the left are the low-voltage version, the ones on the right are the high-voltage version, so there's really not this many needed in any one cabinet. We have a serial interface unit. We have a cabinet power supply, again a 1U format on the bottom right, that provides our internal cabinet power for driving load switches, input files, flash transfer relays, things like that. And on the far right there is the new high-density flash transfer relay, which I'll talk about on a future slide. So this is really maybe the surprise component that we haven't seen before. This is an image of the load switch. So if you can see the detail here, there are two channels on one. Basically, it's a detector-sized card, 1.2-inch width pitch. I believe it's about 4 point something inches tall, has a DIN connector on the back. Very high efficiency, uses FET outputs instead of our older TRIAC technology. So the important aspects of this card are, again, 6 outputs. For each output, we are measuring both voltage and current. So the monitoring system basically knows the power going out to each branch of the field circuit. This information is measured on this card, and it's reported to the monitor via that internal serial bus 3 in the output assembly. So we've sized these components for an LED intersection. We can operate down to approximately 5 milliamp type load range up to 1 amp. Again, this is our notion of being future compatible with ultra low power LEDs. We no longer need leakage current, and we no longer have leakage current. That's how we used to detect, or in a conventional cabinet, how we detect no load conditions. So this eliminates problems that we've dealt with over the years with compatibility between signal monitors and LEDs, and it should help LED manufacturers produce a cleaner, more efficient design. There are some finer details here. We have some blue LEDs on the load switches that we use to help troubleshooting. So we're trying to make every effort to diagnose problems within the cabinet and make them obvious to the technician. Technician's job will still be to determine, do I have a failed component? Do I have a problem in the wiring, things like that. But we have some indicators that are going to help point to the area that the technician needs to address, along with the smart monitor technology in the display unit. So again, this is one of the components that's affected by high voltage cabinet. We have a plug compatible version for a low voltage unit. Again, takes advantage of the low voltage operation in the design of the load switch. So this is a shot of the actual monitoring system. So this is a plug-in card. Couple of things of note. It has a 32-channel capacity. EMA TS2 provides 16 channels, and we've gotten along quite well with that over the years, but we've run into a number of cases where 16 channels just isn't enough, and particularly when we start doing clever things like flashing yellow arrow, we know that those channels get consumed fairly quickly. So 32 channels will give us a capability to efficiently address a number of different problems that we run into. Again, all of the measurement data comes from the load switch itself. The monitor does really the fault processing. You may notice there on the front of the monitor that red key there. It's a non-volatile memory and a data key. So we no longer program monitors with jumpers, diodes, dip switches. Oh my gosh, it's 2015, it's about time. All of the data to program the monitoring system is contained within that interchangeable data key. If we come up with new features, new functions, we don't have to define new jumpers. It's simply database within that key. So because the monitor is small and compact, we have an additional 1U rack-mounted unit that provides the display capability. All of the information that the CMU knows and has is provided either through the Ethernet port to a laptop or a TMC, but it's also sent to the controller unit. So while I think most users will find a built-in display in the cabinet to be very helpful, it is technically an optional product. If you're happy with the information being provided by the controller or through an external device, then that's one less component needed in the cabinet. Let's talk about combat the elements here. It may not be clear in this photo, but in the upper right there is our conventional flash transfer relay in the clear plastic case, which we're all familiar with for the past 30-some years. This particular one is totally filled in with ant carcasses or some kind of insect infestation to the point at which the contacts would no longer make contact because there were so many dead ants in there. It's kind of surprising to me that we've lived all these years with unsealed relays for a component that we basically rely on to always work when something within the cabinet goes wrong or malfunctions. We really want to get that cabinet into the flash mode. So a couple of improvements here with the ATC cabinet. The picture down below is a shot of the relays that were designed specifically for this cabinet by Struthers Dunn, with a number of interesting improvements. First of all is the size. It's very compact. We've retained the same functionality. There are two sets of contacts in here for two separate channels. There is an additional contact that drives, you can't see it in this photo, but on the top of the relay is an LED that actually indicates the contact status. So rather than just telling us that there's voltage on the coil, the LED will indicate to a technician the status of the mechanical contacts. The DC or the coil voltage is already set up for 48 volts DC, so it's another path, the flash drive circuit, that we've converted from high voltage 120 to low voltage 48 volt DC. And again, perhaps most importantly, these relays are hermetically sealed with inert gas inside. That's going to help protect the longevity of the contacts and keep small critters out of there from interfering with the operation. So again, this is an area that we've known has been a problem over the years, and I believe this is a great attempt to, as we said, combat the elements and produce a very highly reliable relay system for transferring the cabinet to flash. I mentioned earlier this notion of, again, the elements, lightning, high voltage surge. The picture in the upper right there is kind of a shot of the main SHA 1250 surge and RFI filter to develop clean power for the internal components. It has, again, LED indicators on it that are meant to assist the technician to determine that this thing has taken a hit and may be in need of replacement. It is pluggable, so we can easily unplug it along with the transient protection devices on the loop inputs, the load switch outputs. We can easily unplug it and test it as part of a preventive maintenance procedure. So again, what level of protection each agency decides to design into their cabinet based on their susceptibility to lightning and so forth, that's up to the agency, but we've got a basic level of protection that I believe all cabinets should contain at a minimum. So surge protection is kind of like insurance. You should buy as much as you feel you need, but this gives us the capability designed in to be able to maintain it in an efficient manner to make sure that when we need it, it will operate. So the summary here, we'll try to wrap up. Again, we tried reflecting back on the original goals that we looked at. We always want to do our best to increase this notion of fail-safer design. So we'd like to know that while the signals are operating, We are detecting malfunctions when they occur in a quick and efficient manner. We are trying to deal with problems that occur after we've detected a malfunction. It's still our obligation to put that intersection into this fail-safer emergency flash level. So there's more work to be done there that I don't have time to cover in this presentation, but we'll see some interesting solutions there for this fail-safer design. It's smart. We've learned very quickly from our experience with NEMA TS2 and ITS cabinet that as more information flows through this cabinet to the different components and between the components, our level of safety, our level of functionality, and our diagnostic capabilities increase dramatically. When TS2 was first developed and published, from the monitoring perspective, this notion of field checking was, in my opinion, one of the biggest breakthroughs for monitoring systems, because it allowed the monitor to communicate with the controller, share information, and determine for the technician what the signal should have been, what the signals actually did, and again, using that information, guide the technician directly to the problem. We have, again, high-density components, so we've tried to address as best we can the need for more space or smaller cabinets. And finally, energy efficiency, LED compatibility, and the ability to migrate to low voltage 48 volt operations if that turns out to be the solution that we need. So we've learned over the years, and we've learned the lesson many times, that if you consider many of these goals, these improvements, these problems, these challenges, if we try and design them in from the start, we end up with a much more robust solution rather than adding them on later. So I think we've done a fairly good job of trying to anticipate and future-proof the design of this ATC cabinet. So let's talk quickly about status. Where are we? I mentioned that the official ITE working group has been on hold. We are currently striving to find funding to reinstate that group, and whether it is hosted by ITE or hosted by NEMA, the goal is to get that back online. What we need to do is finish the standards document. We have a draft version of the document currently. It's all in scattered pieces, so we need a working group environment to bring that together, hammer out some of the detailed design level issues, and publish that as a final standard. So currently there are 2 cabinet OEM manufacturers that are producing ATC cabinets in production quantities, both high voltage and low voltage versions. There are 2 other OEM manufacturers that I'm aware of that are in the design phase and will hopefully be providing prototype and demonstration cabinets in the very near future. We have several projects already deployed. ATC cabinets are new. They are still being developed, if you will, but they are in the stage of early deployment. As far as controller software, the software running in the controllers is basically the same software that's provided for the ITS cabinet version 1, with some relatively simple changes in the messaging format. So at last count, I believe there were 6 manufacturers that supplied local controller software for the ITS cabinet version 1. There are 2 manufacturers that have converted that software to run with the ATC components. And again, the effort to go from version 1 software to ATC software is relatively simple. So as demand builds for this cabinet, I have no doubt that local software vendors of ITS cabinet software will release versions qualified for the ATC cabinet. So we're moving along fairly rapidly. There's still work to be done, but with the interest that we've seen in this cabinet to date, I have no doubt that progress will continue at a fairly rapid pace. I'm personally very excited about the progress that we've made and the advantages that this cabinet brings in many different areas. So I would encourage all of you, if you're not familiar with the ATC cabinet, you've got an overview now, perhaps hopefully enough to get interested, ask some more questions, look into it. I've listed some manufacturers here that are currently participating in this program. There may be others to come, but I would encourage you to contact any of these manufacturers to get more information. Eberle Design is manufacturing the components. The two manufacturers that are in production with cabinets are Intellite McCain. Struthers Dunn provided the flash transfer relays, and Eagle Traffic and Econolite have committed to a design process to get their cabinets up and running. So contact any of these manufacturers. I'll caution you that information on the ITE website in the ATC standards section is not up to date. Again, there was one update done since the working group went on hold in 2011. So there's where the confusion may arise. Everything you'll find on the ITE website still refers to ITS version 2, but again, it's a synonym for ATC. Eventually, when the standards working group is reinstated, we will have an opportunity to update all of that information on the Joint Committee website. So I appreciate the time that you've taken to sit through this overview. We have barely touched the surface of the ATC cabinet and the ATC effort, but I think this is a good opportunity to get an introduction and a quick overview. So I would encourage you to ask some questions. Again, if you send them to through the question tool on the GoToWebinar toolbar, I'll try and compile those, get answers from the experts that are best able to answer them, and we will distribute all the questions and answers. If you want to contact any of the manufacturers directly, I would encourage that as well. So one last notion here, if you're collecting IMSA TARP points, send a quick email to Matt Zinn, mzinn@editraffic.com with your IMSA information. A 1-hour session is worth, I believe, 4 TARP points, so we'll be happy to process that for you as well. So thank you again for attending. This has been a great opportunity to make contact with all of you and present some work that's been done in our industry that I think will go a long way to push the state of the art in traffic cabinets. Have a great day.
Thank you, everybody. And once again, we appreciate your time. I know everybody's busy, and we want to thank Scott Evans again for doing the presentation. Look forward to our next presentation. We do one of these every month, so you'll be seeing emails regarding which product we will be presenting each month. So once again, thanks for your time, and we will respond to all the emails. Thank you.